we've seen the use of Grignard reagents back previously in the alkyl halide chapter. We pretty much just talked about how we made them, said that they're really strong bases. If they're in the presence of anything acidic, they'll pick up a proton, right? Really, the most important use of a Grignard reagent is reaction with a carbonyl compound. So let's just review how Grignard reagents are formed. If we start with an alkyl halide, right, an alkyl or aryl or vinyl, any kind of halide, really. So that chlorine or bromine or iodine can be on a regular carbon, it can be on a benzene ring, it can be on a double bond, doesn't matter. If I add magnesium metal to that, the magnesium will insert itself between the carbon-halogen bond, and that reverses the polarity, right? Normal alkyl halides have a positive, partially positive carbon because the halogen has pulled electron density away from it. The difference is inserting a magnesium there. Magnesium's a metal, so metals are electropositive. That gives us a negative carbon. So that's very important. The Grignard reagent has a nucleophilic carbon, right? Strongly nucleophilic and basic, too. Nucleophiles and bases are very similar. They're both partially negative, but nucleophiles attack carbons usually. Bases attack hydrogen. Otherwise, they act the same way. But we're mostly interested in the nucleophilic properties of the Grignard reagent. So if I have any carbonyl compound, the Grignard reagent will be able to add nucleophilically to the carbonyl. So the mechanism for the Grignard reaction, right, we'll see in just a moment, but it involves a nucleophilic addition, right? I'm going to just make RMgX right there as our Grignard reagent, but that R we'll just assume is the nucleophilic carbon, right? That attacks the carbon of the carbonyl, making an alkoxide intermediate, just like with our reduction, which when I add the acid to it as the second step, protonates the alkoxide and gives us an alcohol. So what we've done here, we have a carbonyl compound, we've made it into an alcohol, just like with reduction, except instead of adding just an H to that carbonyl carbon, we've added an R group. Okay? So ketones become tertiary alcohols. If this were an aldehyde, it would become a secondary alcohol. So it adds one R group, right, to our carbonyl carbon, essentially. Okay? So forming a new carbon-carbon bond right here. It's very important because chemical reactions that form a new carbon-carbon bond are really kind of special. They're sort of difficult to do, and we don't have that many of them. So the Grignard reaction is a very important one to us right now anyway. So let's just take a look at some examples of Grignard reactions. Here I have cyclohexyl magnesium bromide, which we no doubt got from bromocyclohexane, right, with magnesium. So it's cyclohexyl magnesium bromide that reacts just the same as if I were to call that cyclohexane with a C minus, okay, on that one carbon there. Okay, so reacting with formaldehyde, right? It's an aldehyde with just two H's on it. Okay, when we react with formaldehyde, that's what makes a primary alcohol. So to get a primary alcohol by Grignard, we react some Grignard reagent with formaldehyde. Okay, and trace that through. You can see this carbon right here from formaldehyde becomes the CH2 carbon in the product. So we've made cyclohexyl methanol as a product. So that was formaldehyde. If we do just any other aldehyde, Right? Here's phenyl magnesium bromide. That's like benzene with a C- as one of the carbons. Okay, that does the attacking. So here's our aldehyde. Doing that makes a secondary alcohol because the aldehyde had one R group on it already. Okay? Our Grignard reagent adds the second R group. So keep this in check here. Formaldehyde makes a primary alcohol. Any other aldehyde makes a secondary alcohol. Any ketone will make a tertiary alcohol. Here I have ethyl magnesium bromide, which we can just treat like CH3, CH2 with that carbon being negative, right? Dot dot minus essentially. So that carbon attacks the carbonyl, kicks electrons up to make an alkoxide, gets protonated, makes a tertiary alcohol. So we had two R groups on the ketone originally. We added another R group from the Grignard reagent, right? So that's what makes it a tertiary alcohol. So let's do this mechanism. Again, it's just a very simple mechanism. What happens if I have any Grignard reagent, right? That's like a negative carbon. So R minus with MgBr plus as its counterion. For example, methyl magnesium bromide would be CH3 MgBr, or I could do CH3 minus MgBr plus, but it's a negative carbon that's attacking the carbonyl, kicking electrons up. We have an alkoxide intermediate, same sort of thing. The alkoxide, the O minus, is balanced by MgBr plus. Okay. We are able to protonate that then with any sort of hydronium, right? Any form of aqueous acid, we end up with our alcohol. So be very familiar with that. Exact same mechanism as the reduction that we did before. So, right, 2 for 1, one mechanism, 2 reactions. Difference is our reduction had a hydride adding. Our Grignard reaction has a negative carbon that's adding. If I have an ester, a Grignard reagent will add twice to it, just like with the reducing agents. Let's draw this mechanism just real quickly here. Here I have an ester, R C double bond O, O CH2 CH3. And this is an ethyl ester. After adding the first equivalent of the Grignard reagent, what's going to happen? Going to attack the carbon, it'll kick electrons up. Let me just draw the intermediate there. I'm going to call R, right, as the group that was originally on the ester there. So we're going to make R CO minus, OCH2 CH3, that was already on the ester, and then CH3, that's what we added from the Grignard reagent. Here, I better color code. All right. Now, O minus, instead of just protonating there, this O minus will come back down and kick off OCH2 CH3 because that's a good leaving group. Okay. Whenever we have a leaving group on that carbon there, it'll get kicked out. So we end up with a ketone as an intermediate, RC double bond O, CH3, to which the second equivalent of a Grignard reagent can add to. Right? So from there, that's just like the other reaction, right? Our CO minus, CH3, CH3, which we will protonate to get our alcohol. So, same mechanism. The key here is that when I have an OR group already on this alkoxide, the O minus can come back down and kick that leaving group out. Okay? So you end up with a ketone, which the second equivalent of Grignard can react with. So esters, the Grignard reagent, does a double addition. Okay? Well, this looks like a mistake to me. 2-methyl-2-hexanol is this product. That looks like a tertiary alcohol, not a secondary alcohol. So we started out with one R group on this ester plus an O CH2CH3 group. We added the Grignard reagent twice, so that ended up giving us 3 R groups attached on that alcohol. I mentioned before that Grignard reagents are very strong bases. They'll be instantly protonated the moment they're formed if anywhere in our compound or our reaction mixture we have any kind of acidic hydrogen. So the Grignard reagent is protonated by an H attached to any kind of heteroatom like oxygen or nitrogen or sulfur. So an alcohol on NH and SH. If we have a CO2H, right, that's a carboxylic acid. C double bond O, OH. That's an acidic hydrogen. Okay? pK of less than 10 or so, so very acidic. Really, all these have pKa less than 40 or so. So any hydrogen that's remotely acidic will be deprotonated by the Grignard reagent, and we can talk about what would happen there. For instance, let's do this hypothetical molecule, OH CH2CH2. Let's say we made this MgBr. That'll instantly react with the molecule next to it, right, to pull a proton off, right, over onto this basic carbon there. So what we're going to end up with is O minus MgBr plus CH2 CH3. Okay? The problem is this acidic hydrogen right there. So if I have an OH anywhere, it was much more stable for us to have an O minus than to have a C minus. Okay? In order to have a reactive C minus, our solution must be free from any OHs, NHs, SHs, COOHs. Okay? The Grignard reagent will add to any carbonyl compound, also cyanide nitro sulfates. Those all have electrophilic atoms that are attached to double bond O's. Please familiarize yourself with the Grignard reaction, be able to recognize from a product how a Grignard reaction may have been used to form it and so on.